Hey everybody, it's Horner, and let's just go through and talk about some of the things in this lab. When you start the lab, you're going to do several different trials, and on the first trial, you're going to take a disc and you're going to spin it, and as it's spinning, you're going to collect data. So I'm going to start a disc spinning, and then I'm going to collect data on that disc. So you'll notice kind of what's happening as it goes through. You'll see that the velocity is changing. It is actually getting slower because of it starting at a negative velocity and it's going towards zero. You'll see that the angle is increasing in the negative, and that's because I spun this thing clockwise. If you spin it counterclockwise, you'll see that you will get positive values. So I'm going to totally leave that up to you, whichever way you want to spin it. If you spin it the opposite way, obviously you're going to get a positive graph that's going to start getting closer and closer to zero. For your report sheet, you want to make sure you read all the directions to begin with, but for your report sheet, it says examine the WT graph. So this right here for your runs with a single aluminum disc, which I just did. And you're going to do this with another disc too. They want you to find the rate of change of the angular velocity for each disc as it slowed. So really that's pretty simple to do. We need to use this graph of the one down on the bottom. This is the velocity in radians per second. And what I want to do is I want to find the slope of that line. So you just click on the graph down on the bottom, and then you just say apply curve fit and do linear and say apply, and it will give you your slope. And you'll see that my slope here is 0.6502 and it's negative. So that's going to be my rate of change of angular velocity. So it's just negative 0.6502. And then remember that that is in radians per second. So I'm going to do that one, and then I'm going to do it for the steel, and then they have a couple of questions for you to answer. They want to know why it slows down. It should be super obvious. Should be super obvious. When we go to the next one, this is number 3. You're going to start your disc spinning again. So I'm going to start my disc spinning, and then I'm going to collect data. And you'll notice that disc is going, and then I'm going to drop another disc on top of it. And when I do that, you'll notice that we have a big blip in the velocity radians per second. So they want us to do a couple of things. They want the angular velocity before the mass is added and the angular velocity after the mass is added, and they want the change in time for that to happen. So to do that, you'll want to select the data in the velocity versus time, and you'll just want to select on either side of that sharp drop because your velocity dropped. Then at that point, you want to zoom in, and once you zoom in, you can see a little bit better what's happening. You'll notice that right at this point, that is where our speed really starts to decrease. Now, some people may say that it's maybe over here, but if you look at it all together, so I'm going to get rid of this, you'll see that there is a decrease. So if you want to start right here, you sure could. You'll want to record both the radians per second and the time. Then you're going to do it on the other side of that dip. And so on the other side of the dip, I have a new time and a new radians per second. You'll have to go through and do the, put in your original value here, your final value here, and then that change in time. Once you've done that, you're set, and you'll be able to go through and do the math for the next part. So angular momentum of a system is the equation L, which stands for angular momentum. So this is angular momentum. And then we have I, and you remember I is your moment of inertia. And you're going to find that earlier. And then omega, remember, is just your speed. It's your angular speed though. So don't forget it's in radians per second. Angular speed And so this is very similar to linear momentum. Remember, linear momentum is equal to mass times velocity. So angular momentum, linear momentum. Your mass, remember that is inertia. Mass is inertia is a property of matter. And then finally we have our speed. So really not a different equation at all. Those are the same. And if you remember, we also said that your original momentum, when you conserve momentum, should be equal to your final momentum. So I know that that's m original, v original should be equal to m original times my v final. When I do this for the angular, I know that my angular momentum initial should be equal to my angular momentum final. And so that is my I for my disk times the angular speed original should be equal to I times my angular speed final. If I have a collision, then I know that I need to add all of my angular momenta. So if I have a steel disc, so I have a steel disc, and I add that to an aluminum disc, I have to then figure out, do I conserve momentum? So I would do the I for the steel disc times its original speed plus I for the aluminum disc times its original speed, and that should be equal to I for the steel disc plus the I for the aluminum disc, and then we just multiply that times our final angular speed. Because remember, this is a perfectly inelastic collision where they stick, and because they stick, then we can use this equation. So hopefully that is helpful. Here, they want you to go through and actually go through, they want you to find the change in speed due to friction alone, okay? And so you'll be able to do that. There is a third run that you have to do, so you're gonna wanna go through and make sure that you save all your runs. So going back, this one was run 2. And so when you save these, you'll wanna go to Save As, and then I would save these as whatever period you are. So period 1, and then gold, and then I want to say run 1. And I'm going to click save. That way I've got each one of these. Now when I do a new one, I'm going to say new experiment. I'm going to go in, I'm going to select it. It's going to take a second here. And now I can do my next one. And I'm going to call this one run 2. And then I'm just going to keep going through. That way, if you need to go in and open any of your runs, you'll be able to go in and open them and go back and look at your data. So it might be good to go through, do all of the runs first, and then go back and do your analysis. And that is it.